Let me introduce our speaker today, Marc Kamionkowski, who is a William R. Cannon Jr. Professor at Johns Hopkins University. He got his PhD in 1991 from the University of Chicago. He was a member of the Institute for Advanced Studies between 91 and 94. And then he got an assistant professor position at Columbia University, where he was promoted to an associate professor in 98. And in 99, he moved to California Institute of Technology, where he became a professor of theoretical physics and astrophysics. He also became, in 2006 at Caltech, a founding director of the Moore Center for Theoretical Cosmology and Physics. At the same time, he was also a Robinson Professor of Theoretical Physics and Astrophysics. In 2011, he moved to Johns Hopkins University, where in 2016, he became William R. Cannon Jr. Professor of Physics and Astronomy. So he has numerous awards and honors. I will not be able to list them all, but let me briefly mention that he's a member of U.S. National Academy of Sciences, American Academy of Arts and Sciences. He's a Legacy Fellow, American Astronomical Society, Fellow, American Association for the Advancement of Science, Fellow, International Society of General Relativity and Gravitation, and Fellow, American Physical Society. In 2015, he received Danny Hyman Prize for Astrophysics. And he's also very active in professional service. Among many things, I will probably mention only one thing. He is the editor-in-chief of the Physics Reports, one of my favorite review journals. So with that, I will give the microphone to Marc. And everybody else, please mute your microphones.
So thank you very much. Glad to hear. Is Physics Reports in the top 10 of your favorite physics review journals?
Yes, founded by Jerry Brown.
Yep. So I see that there are a lot of people on the call whose names I do not recognize, and some people whose names I recognize, but I know they work in other areas of physics. And so I'm going to begin by apologizing that this talk might be aimed a little bit more for a specialist than I should have, but we'll see. Feel free to ask me questions. Usually the answers to questions are more illuminating than the things that I might just be telling you otherwise. And it's also good to have questions because it's hard to keep an eye on you and see you know, whether you guys are nodding or nodding off or lost or whatever. So the title of the talk is Chirality and Cosmology. And this talk is sort of related to a variety of things that I've done over the years related to this question, but it's focused primarily on things that I've done most recently. So the genesis of this line of thought comes from the observation that the weak interactions that appear in nature are parity-breaking. We have left-handed neutrinos, but no right-handed neutrinos. It's only the left-handed components of the leptons that interact with the W and Z bosons. So, you know, nature does not respect parity. Now, in cosmology over the years, we've had a number of discoveries and observations that indicate that there is new physics that is required to understand what's going on in the universe. So, for example, there is dark matter in the universe. About, you know, for every baryon and for every GeV of mass in the universe in a proton, there is roughly 5 or 6 GeV in mass in some unknown dark matter. And we have no idea what it is, but it's pretty clear that it requires new physics beyond the standard model. The expansion of the universe is accelerating rather than decelerating. And if all the matter that we saw in the universe was all that there was, we would expect the expansion rate to be decelerating because gravity is an attractive force. So if galaxies are flying apart from each other at some velocity today, according to, you know, the inverse square law, that velocity should be decreasing with time. But we see that the velocities, the relative velocities between galaxies is actually increasing with time today, which suggests that there's something like an anti-gravity, or what we often refer to as dark energy. Or maybe there's some alternative theory for gravity that we don't know about. Maybe there's something more to gravity beyond general relativity. There are baryons in the universe, but no anti-baryons. So there is a baryon asymmetry. We see lots of protons and neutrons, but no antiprotons and no antineutrons. And again, we don't really know why that is, but it does require that there's be new physics beyond the standard model, new physics that involves breaking of time reversal invariance and or CP invariance. And then finally, there is the early universe. We see correlations in the distribution of galaxies in the universe and correlations in the distribution of temperature fluctuations in the early universe that indicate that there were causal processes happening on distance scales larger than the distance scales that are in causal contact in the standard cosmology. And in order to explain that, we again need some new physics beyond the standard model. So it is natural to inquire, given that the weak interactions are parity breaking and that there is new physics required to explain some of the things that we see in the universe, it's natural to inquire whether that new physics also manifests parity breaking. And so this is something that I've been interested in over the years. Is it possible to discover or search for parity breaking effects in cosmological observations? And are there new physics models for dark matter, dark energy, baryogenesis, or the early universe in which would leave signatures of parity breaking? So that sort of motivated a variety of work that I've done over the years. And as you'll see in this talk, thinking along these lines has been valuable not only for these questions about new physics beyond the standard model, but in some cases, thinking along these lines has actually led to new ideas for ways to use astrophysical observations to understand traditional astrophysical objects like neutron stars, stars, black holes, and galaxies. So this is what I just told you. Inflation, dark matter, dark energy. Are these things parity breaking? So that's the gist of the talk. Some of the themes of this talk are elegant mathematics, some proofs of principle, and also new observables. So this is theoretical work. As you will see, some of this theoretical work is motivated by the desire to apply some mathematical tools that some collaborators and I developed. Some of the work is aimed at providing proofs of principle for new ideas, even though they may have nothing to do with actual astrophysical or cosmological observations. And as we will see, there will also be some new observables that come out of these. And some of these are fairly futuristic or for academic purposes only. But some of the things that I'm going to be discussing are actually going to be observable with measurements that are to be done over the next 5 to 10 years. In particular, I'll be talking about the cosmic microwave background, the relic gas of photons left over from the Big Bang, the afterglow from the Big Bang. And I will talk about the circular polarization of the cosmic microwave background. And my guess is that you have never heard a talk about the circular polarization of the cosmic microwave background. I'll talk about circular polarization of the cosmic microwave background that should arise from physics that we know is there from the primordial density perturbations that we see in cosmic microwave background maps. I will talk about circular polarization from things that we speculate about but don't know are there, in particular a gravitational wave background from the early universe, and in particular from a gravitational wave background that is chiral, that distinguishes between right and left-handed gravitational waves. I'll also then talk about a stochastic background of primordial gravitational waves that exhibits chirality, again, an asymmetry between right and left-handed gravitational waves. And I'll talk about how we might be able to detect such chirality with pulsar timing arrays and with astrometry. And I'll tell you about pulsar timing arrays. Astrometry is just measurement of the angular positions of stars, very precise measurement of the angular positions of the stars. Astrometry is the science of where things are in the sky. And then I'll also talk about 21 centimeter polarization. As you know, neutral hydrogen has a transition between its ground state and its first excited state, and its first excited state is separated from the ground state by a very small energy gap. And the photon that's emitted in that transition has a wavelength of 21 centimeters or a frequency of 1.4 gigahertz. And that is the transition that occurs when the the proton and electron spins flip. So it is the separation between the spin triplet and spin singlet of the proton and electron. And it turns out that people are trying to detect that 21 centimeter polarization from neutral hydrogen in the early universe. I have benefited in this work, like in all my work, with very good collaborators. One of them is Keisuke Inomata, who just finished a PhD at the University of Tokyo and was supposed to be in Baltimore for a visit this summer, but that didn't happen for reasons you can guess. He's going off to a postdoctoral position at the University of Chicago this fall. The work I'll talk about with pulsar timing arrays in astronomy is done with Salim Hotinli, who's a graduate student at Imperial College, who will begin a postdoc position at Baltimore. Kim Body, who until today has been a postdoc at Johns Hopkins and is today flying to Texas to begin a faculty position at UT Austin. Wenzer Chin was an undergraduate at Johns Hopkins. She's now a graduate student at MIT. Liang Dai was a student of mine, and he has been a postdoc at the Institute for Advanced Study for the past 4 or 5 years, and he is moving to a faculty position at UC Berkeley this fall. Andrew Jaffe is a longstanding collaborator of mine at Imperial College. Enes Belgasem is a student in Geneva who came to visit and work with me last year. Ling Guangji is a graduate student at Johns Hopkins. He did the work with me on 21 centimeter. And as you'll see, all of this work actually benefits from a mathematical formalism that we call total angular momentum waves, TAM, total angular momentum, that was developed with Liang Dai and also Donghui Zhang, who at the time, about 10 years ago, was a postdoc with me, and he's now a faculty member at Penn State University. So, hold on, did I miss a slide? I did miss a slide, huh? Okay, I'm missing a few slides, but it's not too significant. So usually when you hear about the cosmic microwave background, you hear about temperature fluctuations that have been measured precisely with the Planck satellite and the WMAP satellite. And to a first approximation, the temperature of this cosmic microwave background, which comes from all directions on the sky, is roughly the same, but there are fluctuations in temperature of roughly 1 part in 10 to the 5. And then more recently, it was found that the cosmic microwave background is linearly polarized. And we've now mapped the linear polarization of the cosmic microwave background as a function of position on the sky fairly precisely. And that linear polarization was expected, and it arises because of anisotropic Thomson scattering of cosmic microwave background photons from electrons. When you have light that scatters from, Thomson scatters from electrons, it becomes polarized, linearly polarized. And so the linear polarization just arises because this light that we see, the last time it scattered, it was scattered from free electrons in the early universe. Circular polarization is something that you probably haven't heard about in connection with the cosmic microwave background. And the reason is that it does not arise at linear order in the cosmological perturbations. So I told you that, when we look at a cosmic microwave background photon, the last thing that it did was Thomson scatter from an electron. And Thomson scattering does not induce circular polarization. However, it is possible that you can have circular polarization generated if a linearly polarized photon passes through a medium with an anisotropic birefringence. Sorry, a medium with an anisotropic index of refraction, or in other words, a birefringent medium. And the slide I'm missing is the picture that I had of this. So you have to imagine a cosmic microwave background photon that's propagating towards us. It propagates for 13.8 billion years. And as it propagates through the gas of all the other photons in the universe, in the cosmic microwave background. And in the standard classical electromagnetic theory, photons do not scatter from each other, but there is, in quantum electrodynamics, an Euler-Heisenberg Lagrangian that arises at the next non-vanishing order in perturbation theory in quantum electrodynamics. So the standard, classical electromagnetic Lagrangian, E squared minus B squared, gets augmented in perturbation theory to order alpha squared by terms that are quadratic, that are quartic in the electric and magnetic field. So there's an E squared minus B squared and an E dot B squared. And that gives rise to a Feynman diagram that allows one photon to scatter from another photon. So what we imagine is that one of these photons is the cosmic microwave background photon that we're looking at, and the other is a photon, some other photon from the cosmic microwave background. Now, when we look at the cosmic microwave background, we see intensity fluctuations. The temperature from some region of the sky is different than the temperature in some other regions. And that is true generically at any point in the universe. So when some photon is passing through us, it is propagating through an anisotropic radiation field. And that anisotropic radiation field gives rise through this Euler-Heisenberg term, this photon-photon scattering, to an anisotropic index of refraction that a given cosmic microwave background photon passes through. This was identified by Ray Sawyer in 2014 and worked out very nicely by Montero and Camacho and Harada in 2018. So this is how circular polarization arises. Now, it's going to be a small effect because this alpha squared is small, and the density of cosmic microwave background photons is also small. So this is going to be a small effect, but it's a calculable effect, and it's interesting to follow through with the calculation. Oh, here's the picture. So here's the picture of the cosmic microwave background. These are the temperature fluctuations. This is actually the map that that comes from WMAP or Planck. I actually don't remember which one this is. So they're hot and cold spots. Some regions of the sky are hotter. Some regions of the sky are colder. And there's also the linear polarization that was induced by Thomson scattering that's also been detected. So in some regions, linear polarization looks like this. In some regions, it looks like this. Now, the circular polarization does not arise at linear order in cosmological perturbations because, as I said, Thomson scattering induces only linear polarization. And that linear polarization arises when that cosmic microwave background photon that we're looking through has propagated through a birefringent medium. So this is the mathematics that we use to describe the circular polarization and the linear polarization. So suppose I look at a photon coming at me from some direction, some line of sight, hat n. The linear polarization of that photon is described by two Stokes parameters, Q and U. And those Stokes parameters are components of a symmetric trace-free 2x2 tensor, which I call PAB of n, where A and B are indices that live on the two-dimensional surface of the sky. So when I map the polarization as a function of position on the sky, I am mapping a symmetric trace-free tensor, a symmetric trace-free 2x2 tensor that lives on the surface of the sky. That's a function of position on the surface of the sphere, the celestial sphere. Now, the birefringence or anisotropic index of refraction is described by an index of refraction tensor. So the components of the CMB, of the polarization that are aligned with the Q Stokes parameters are going to be propagating at one velocity and experience some phase lag phi sub Q, whereas the scattering from the anisotropic cosmic microwave background photon field will give to another index of refraction phase, or another phase, due to the fact that the photons with the U Stokes parameter polarization might have a different velocity of propagation. So this is the anisotropic index of refraction, or actually strictly speaking, this is the anisotropic phase lag. So phi sub q is the phase lag for the q component, and phi sub u is the phase lag for the u component. And that phase lag in the q and u component is an integral along the line of sight that the photon travels along of the frequency of the photon, but more importantly, the index of refraction for the photon, for the q component and the u components of the Stokes parameters. And then the circular polarization in the direction n turns out to be a tensorial cross product of the linear polarization with the index of refraction tensor. So this is the linear polarization of the photon initially, and then this is the phase lag tensor, the index of refraction phase, the phase tensor for the two different components of the linear polarization. And the epsilon arises because the circular polarization V is what's it called, a pseudoscalar that's constructed of two symmetric rank-free 2 by 2 tensors. And so if we do a parity inversion, this pseudoscalar is going to change sign. And so we know that it has to be something like a cross product between the polarization tensor and the index of refraction lag. The other thing is if these two, PAB and phi, if these two tensors are aligned, there will be no polarization induced. The circular polarization is induced by a misalignment of PAB and phi BC. And so that's why we have this tensorial cross product of the polarization and the index of refraction tensor. So it turns out that the linear polarization generated by primordial density perturbations in the early universe, so the linear polarization that we have observed and measured and that we understand, is generated by primordial density fluctuations in the early universe. And what that tells us is that the linear polarization tensor is a linear combination of the E-mode linear polarization spherical harmonics. So this PAB is a symmetric 2 by 2 symmetric trace-free tensor field that lives on the surface of the sky. It has 2 degrees of freedom because it's described by 2 parameters, Q and U. And so it can most generally be linearly decomposed into 2 different types of tensor-valued spherical harmonics, or tensor spherical harmonics. So AB tells us that this is a tensor that lives on the 2 sphere. So YE is a symmetric ring-free tensor valued spherical harmonic. And it's one of 2 types of tensor spherical harmonics. The other one is a B mode, which I don't include here. But it turns out that the B mode has opposite parity of the E mode. And we have shown in prior work that primordial density perturbations produce only the E mode. And so when we look at this linear polarization pattern in the cosmic microwave background, it is a linear combination of these E-mode tensor spherical harmonics only with coefficients PLM. And the same is true for the index of refraction tensor, or actually should say the phase lag tensor. It's also a linear combination of these E-modes. And so if I take this tensor spherical harmonic expansion for PAB, this tensor spherical harmonic expansion for phi AB, and use this formula over here, it turns out that the spherical harmonic coefficients for the V, so if I expand this V in terms of spherical harmonics, the spherical harmonic coefficients can be written in this way. So it involves a sum over all of the polarization spherical harmonic coefficients, the phase lag spherical harmonic coefficients, and then this product of an integral over 2 of these tensor spherical harmonics and an ordinary spherical harmonic. And it turns out that we know how to do this integral. And so the power spectrum, the angular power spectrum for the V-mode circular polarization winds up being something that you can write in this fairly simple and economical way. And I should say that this result was derived, actually was not derived in the earlier paper. It turns out that this result is very easy to derive using this formalism, and in prior work, something like this was derived with much, much more labor using the standard Fourier formalism instead of these total angular momentum wave formalism. So it turns out that we have a prediction for a power spectrum for the circular polarization. It depends on the power spectrum for the primordial linear polarization, on the angular power spectrum for the phase lag. And interestingly enough, we have this minus sign here, which tells us that if the phase lag, this is the cross correlation between the polarization and the phase lag. If the polarization and the phase lag were perfectly cross correlated, if they had the same pattern, then this cross correlation, this product over here would have the same magnitude as this product over here, and it would be 0. So in the limit that the polarization and the phase lag tensors are aligned, the circular polarization goes to 0 as it should. And this thing over here is something that is related to Wigner 3J symbols. So it's something that Mathematica knows how to calculate, for example. Now, we do not know that there are gravitational waves left over from the early universe, but many theories of inflation do predict that there should be some stochastic background of primordial gravitational waves. And so great efforts are being made to look for these primordial gravitational waves. Now, it turns out that if gravitational waves exist, they also can induce linear polarization in the cosmic microwave background. But in addition to these E modes, gravitational waves also produce the B modes. So the linear polarization due to gravitational waves involves a sum over E modes, and then a second term that involves a sum over B modes. So instead of this very, very simple result that we have for the circular polarization, if they're primordial gravitational waves, the result is a little more complicated, because now we have terms that involve E modes, but also terms that involve the B modes, as well as cross correlations between E modes and B modes. So this was derived in a paper I wrote with Keisuke Inomata, and it turns out that although the results look a little complicated, again, the derivation is fairly straightforward using the total angular momentum formalism. And these results are not necessarily that interesting. And the reason is that the circular polarization, as I told you, turns out to be very small. First of all, the density of cosmic microwave background photons is very small, but the probability for 2 photons to scatter is very, very small, because this Euler-Heisenberg-Lagrangian is quadratic in the fine structure constant. So it turns out that the circular polarization from primordial density perturbations is 8 × 10⁻14 Kelvin, and from gravitational waves, in the best case scenario, 2 × 10⁻17 Kelvin. This should be contrasted with a temperature fluctuation amplitude of 10⁻5 Kelvin, and the polarization, linear polarization amplitude, which is around 10⁻6 Kelvin. So this is, somewhere between 8 and 11 orders of magnitude beyond current capabilities. So this is, I would say, a proof of principle rather than a prediction for experimentalists to try to go out and measure anytime soon. There is something interesting, though, conceptually. So some models for inflation predict not only that there is a gravitational wave background, but also that that gravitational wave background is chiral. In other words, that there is a preponderance of right-handed gravitational waves over left-handed gravitational waves, or vice versa. Now, the photons in the cosmic microwave background are not chiral. There is no reason why we should have more right-handed photons than left-handed photons. But the point of this second short paper that Keisuke Inomata and I wrote was to show that through this Euler-Heisenberg-Lagrangian, if there are primordial gravitational waves that are chiral, the chirality of the gravitational waves can be imprinted on the circular polarization of the photons. So, I won't go through the derivation, but just sort of walk you through the results. So V00 is the monopole of the circular polarization. So this is the L equals 0, M equals 0 mode of the circular polarization. So if V00 is non-zero, it means that when I average over the entire sky, I am seeing more right-handed circularly polarized photons, left-handed circularly polarized photons, or vice versa. And this is the formula that we get for the this is our prediction for the expectation value of that circular polarization. And it turns out to involve a cross correlation between the E mode of the polarization and the B mode of the index of refraction tensor. Now the E modes and the B modes have opposite parity. And so a cross correlation can arise only if there's parity-breaking physics. And that parity-breaking physics is the chirality in the gravitational waves. And it turns out that chiral gravitational waves actually do produce these cross correlations. So in this paper, we were able to show that if there is an asymmetry in the number of right versus left-handed gravitational waves, that's what this delta chi is. Delta chi tells us the fractional asymmetry between right and left-handed gravitational waves. If there's a gravitational wave chirality, it will introduce a circular polarization in the cosmic microwave background. And the amplitude is dependent on the amplitude of the gravitational wave background. Here, R is the amplitude of the gravitational wave background in units of 0.06, the current upper limit that it can take. Now, I'm confused because I'm confused by why I have this formula here as well, which is not the same as this formula and incorrect. Anyway, sorry. So ignore this formula over here. Now, there's something interesting, something else that's interesting. Suppose we have a gravitational wave background, but it is not a chiral gravitational wave background. The circular polarization that we wind up seeing from gravitational waves is going to depend on the random realization of gravitational waves that appear in our universe. So if there is a chiral gravitational wave, a gravitational wave background that's not chiral, it is still possible for there to be a non-zero circular polarization. So this is the formula for V00, the monopole to circular polarization, and it depends on a sum over L and M of this combination of the E mode polarization and the B mode index of refraction tensor. So in general, the cross correlation between these is 0 if there's no chirality, which tells us why the expectation value for V00 should be 0 if there's no chirality. But in any given random realization of the gravitational wave background in any observable universe like our own, we can calculate the expectation value of V00 squared. So even if the expectation value of V00 is 0, even if there's no chirality, the expectation value of V00 squared can be 0. In other words, even if the expectation value of V0 is 0, it is possible that in our observable universe, we would measure a value that is non-zero. And heuristically, this can be understood because even if I have a chiral gravitational wave background, the number of gravitational wave modes that actually affect the circular polarization that we observe might be finite, maybe 100 gravitational wave modes. And on average, 100 of those gravitational wave modes will be right-handed, and on average, 50 will be right-handed and 50 will be left-handed. But in any given realization, I will have 50 plus or minus the square root of 50, say maybe 55 right-handed gravitational waves and 45 left-handed gravitational waves, just because of random, Poisson fluctuations in the number of right versus left-handed gravitational waves. So one of the interesting things that we discovered in this paper is that it is possible that we would measure a circular polarization, a non-zero circular polarization for cosmic microwave background photons if there were gravitational waves, even if those gravitational waves were not chiral. And only if we observe V00 to be larger than this RMS value, 3 times this RMS value, would we be able to establish a chiral gravitational, the existence of a chiral gravitational wave background. So that's all I have to say about circular polarization of photons. We also thought about whether we might be able to detect gravitational waves and chiral gravitational waves with pulsar timing arrays. So this is a very exciting area of astrophysics and gravitational wave science. This is a plot of the gravitational wave amplitude or gravitational strain as a function of the gravitational wave frequency that is predicted by a variety of astrophysical sources. So the mergers of stellar remnant black holes gives us gravitational waves with frequencies around 100 hertz. And this is the sensitivity of LIGO, and these are the gravitational wave events that LIGO has detected. Supermassive black holes are expected to produce gravitational waves that have frequencies in the range around 10 to the minus 2 hertz. And those mergers are hoped to be detected with LISA, which is a European Space Agency satellite that will hopefully launch within the next decade and a half or so. But there's another thing. These supermassive black holes, before they merge, will be spiraling around each other for a long time. And as they spiral around each other, they emit gravitational waves. And the gravitational waves that they emit have a broad range of frequencies, but they will emit gravitational waves with frequencies around 10 to the minus 9 hertz, or with periods of several years. Now, it turns out that there are things called pulsar timing arrays that work more or less in the following way. So if we are here observing on Earth, we observe a bunch of pulsars. Pulsars are neutron stars that spin and emit radio pulses as they spin. And we observe these radio pulses, and we can therefore observe the spinning of these neutron stars. And these neutron stars are extremely heavy, and so they have very high moments of inertia, and so they are very, very steady rotators, and so the pulses they emit are extremely reliable clocks, very steady clocks. Now, if a gravitational wave passes through the solar system, that will distort the space-time metric, and that will give rise to time delays in the arrival times of the pulses from these different pulsars. And the idea of pulsar timing arrays is to observe the pulse arrival times from pulsars spread throughout the sky, and then compare those pulse arrival times with each other. And if a gravitational wave passes by, then the relative arrival times of pulses from these different pulses will be affected, and we'll be able to see that in that pulsar, in the arrival times of those pulsars. Now, the observations are done roughly every 2 weeks. They observe each pulsar for roughly 30 minutes every 2 weeks. And then they do these measurements over a decade, several years to decade time scale. And so that's why the frequencies that we can observe, the gravitational wave frequencies that we can observe, are up to about 10 to the minus hertz, roughly 10 years to 10 to the 6th, 10 to the 7th hertz, which is more of the periods associated with several months or several years. So it turns out that pulsar timing arrays are very close to having the sensitivities that we expect to see from these merging supermassive black holes. So I'm not going to go through this calculation very carefully, but I'm just going to advertise work that I did with Liang Dai, Wenzer Chin, and Kim Body. And the point of that work was to rederive the predictions for the timing pulse arrival time correlations as a function of the separation angle between the two pulsars that you're correlating. That's this capital theta, using a total angular momentum formalism. So I'm not going to go through the derivation, but I will just advertise that in this work, we were able to derive this old result, this Helling-Stauns curves, which goes back 40 years, maybe more, late 60s, early 70s. So it turns out that the correlation, so here X is cosine theta, the correlation between the pulse arrival times was derived, many years ago to be this relatively simple formula, but it was derived through very complicated calculations. And what we're able to show in this paper is that using this total angular momentum formalism that Liang Dai and Donghui Zhang and I derived a few years ago, the result appears in a few lines as opposed to pages and pages of algebra. The same thing, not the same thing, it's also been noticed recently that we could also detect gravitational waves not by using pulse arrival times, but also using the positions of stars. So as a gravitational wave propagates through the solar system, it will wiggle the locations of stars on the sky. And so that is shown in this figure that was generated by Moore from the University of Cambridge, Christopher Moore from the University of Cambridge. This is a simulation of the deflections of the angular positions of stars on the sky when a gravitational wave propagates through the universe. So again, the idea is to take pictures of the locations of tons of stars in the sky throughout, across the entire sky, and then do that every, 2 weeks if you can, or as much, as often as you can, and then to compare the images of the sky at different times and see whether the stars are wiggling back and forth with this characteristic pattern induced by gravitational waves. And again, the mathematical formalism that we use to derive this pulsar timing array prediction can be used to derive predictions for the angular deflections of these stars in astrometry surveys. And again, there's some mathematics to describe it. And in the standard approach, you describe gravitational waves in terms of Fourier coefficients. You describe gravitational plane waves. In the total angular momentum approach, you describe gravitational waves as a sum over, instead of using Fourier modes as the normal modes of the system, use things psi KLM that we call total angular momentum waves. A plane wave is an eigenstate of the spatial translation operator. It's, whereas the total angular momentum waves are eigenstates of angular momentum, which is a consequence of the rotational invariance of the Euclidean space of the universe, as well as a spatial translation in a given direction, which is given by this wave number k. Again, I'm just advertising the mathematics, not explaining it. And as I say here, it turns out that the total angular momentum formalism turns out for this particular calculation to be very, very powerful and allows you to derive results for the pulsar timing array and astrometry predictions very, very simply and elegantly. And just to advertise, the results for pulsar timing arrays and for astrometry experiments for general relativity, as well as just about any imaginable alternative gravity theory, can be summarized in this one formula over here in terms of these transfer functions f, which we calculate here for the most general gravitational wave. So TE and TB are the standard gravitational wave polarizations in general relativity, the transverse tensor polarizations. But in alternative gravity theories, you can have gravitational waves that have vector polarizations or scalar transverse or scalar longitudinal polarizations. And so the results for any alternative gravity theory, any of these polarizations for astrometry and pulsar timing arrays is provided by these two simple formulas. And if you look at the prior literature, these results are derived in prior literature, but each one of these results winds up being derived in very, very complicated ways. I'm going to go through this very briefly, given time limitations. Again, I'm just going to advertise more recent work that I did with Enes Belgesem and also more recent work with Ling Guanji and Enes Belgesem. We've also been able to use tools adapted from this total angular momentum formalism to develop an algorithm to look for gravitational wave anisotropy with pulsar timing arrays. So again, imagine I have a pulsar timing array. What that means is that I'm collecting the arrival times of trillions of pulses from pulsars throughout the sky. And then I'm trying to use the relative arrival times of those trillions of pulses from all these different pulsars spread throughout the sky. And right now we're talking on order 100 pulsars that are being used for these surveys. We use those pulse arrival times to infer the existence of gravitational waves. And what we've been able to do in this new work, and here I'm just showing you the formulas, is to come up with an algorithm which is summarized in these formulas, to take that data and not only detect a gravitational wave background, but to figure out whether there are anisotropies in the flux of the gravitational wave background. We've been able to figure out how to take that data and determine whether the gravitational wave, the intensity of gravitational waves coming from this side of the universe is different than that coming from this side of the universe. And we've also been able to figure out how to infer the circular polarization of these gravitational waves. So again, the formulas are complicated but straightforward, and they involve lots of tools that you may remember from quantum mechanics. Wigner rotation matrices make appearances here. Wigner 3J symbols make appearances in here. But the bottom line is that if the intensity of the gravitational wave background is expanded in terms of spherical harmonic coefficients, so if capital L is 1, for example, and M is 0, that would mean that there is a stronger gravitational wave signal coming from the North Pole than from the South Pole. So these GLM parameterize the intensity of the gravitational waves as a function of direction of the sky. We've been able to write down estimators for these estimators, quantities that you can compute from the data to calculate those anisotropies, to infer those anisotropies, and also circular polarization. And again, we can use these estimators to figure out whether there is a circular polarization in the gravitational wave background. Although it turns out that, curiously enough, for reasons that are similar to the derivation of the Li-Yang theorem for the decay of a massive spin 1 boson to 2 photons, for selection effect reasons similar, and other selection effects that you get in nuclear decays, for reasons similar to that, the behavior of the properties of the Wigner 3J symbols that come into this can be used to show that you cannot use this to detect a chiral gravitational wave background. We can, with pulsar timing arrays, figure out whether the gravitational waves coming from that direction are circularly polarized, and those coming from the other direction are circular polarized in a different way, but we cannot detect a monopole of the circular polarization of the gravitational wave background. We cannot detect an overall asymmetry between right and left-handed gravitational waves. It turns out that the tools that we've described here are not just for academic purposes. It turns out that there is a gravitational wave background from the mergers of supermassive black holes. And when supermassive black holes spiral in and emerge gravitational waves, those gravitational waves will most generically be circular polarized. Now, if you are observing a supermassive black hole binary that's spinning around like this, you are going to see a time-varying quadrupole moment, mass quadrupole moment, or gravitational field. And so the gravitational waves that you see will be circularly polarized. So we're almost sure that there has to be a nanohertz gravitational wave background from the mergers of supermassive black holes. And we know that that gravitational wave background has to be circularly polarized to some degree. And we also know that the local signal has to be anisotropic, because the signal is likely to be dominated by a handful of nearby supermassive black hole mergers. So the tools that we've developed in this work are actually going to be useful for experiments that are being done and that will be done over the next, with much greater sensitivity over the next 10 years. So to close, I just wanted to mention one last thing that we finished. Actually, this is no longer in progress. We have finished the paper now. There is 21 centimeter radiation, as I said, from neutral hydrogen during the dark ages. So the time after electrons and protons combined to form hydrogen atoms, 380,000 years after the Big Bang, until a few 100 million years after the Big Bang, when stars first formed, the gas in the universe consisted of neutral hydrogen. And that neutral hydrogen could have absorbed or emitted 21 centimeter photons through this 21 centimeter transition from the spin flip transition of neutral hydrogen. So it turns out that Hirata, Mishra, and Venumatov have calculated the circular polarization of the 21 centimeter transition from neutral hydrogen that arises from primordial gravitational waves. And in our new work, we have reformulated their calculation in terms which was done in terms of Cartesian tensors into the total angular momentum formalism. And we were able to rederive and then generalize their results. And what we did in this paper was provide the first results on the standard model prediction for the circular polarization of the 21 centimeter transition. And by standard model prediction, I mean the prediction for the circular polarization that should arise from second order in the primordial linear density perturbation amplitude. So this is a prediction, and it turns out that it is small, but not inconceivably small. The physics is described here. So suppose I have one Fourier mode of the primordial density field. So there are dense regions of the primordial density, dense regions in the early universe, less dense region, more dense, less dense. And suppose we live in this underdense region, then, suppose a neutral hydrogen atom lives in this underdense region. The intensity of 21 centimeter radiation that it sees from here and from here will be different than it sees from here and here. But it also sees an anisotropic quadrupole of the cosmic microwave background. So the cosmic microwave background last scattering surface is bigger, and so there'll be a cosmic microwave background quadrupole that probes the distribution of mass, the anisotropic distribution of mass on a larger surface. And this quadrupole can interact with the quadrupole of 21 centimeter flux to produce a circular polarization. So again, there is a formula for the circular polarization observed in some direction n, and it involves something like a cross product between the temperature fluctuation, the cosmic microwave background temperature fluctuation, and the 21 centimeter radiation fluctuation. This is the quadrupole of the 21 centimeter. This is the quadrupole of the 21 centimeter radiation. And those interact to give rise to a circular polarization for the scattered radiation. And we have now finished this paper. This is our result. It looks long, but trust me, compared with the standards, other papers in the literature with doing similar calculations, this, to our eye, if not to anybody else, is an extremely simple and elegant and compact expression. And it turns out that it is interesting. This is the numerical predictions for the circular polarization angular power spectrum as a function of the multipole moment at different observer frequencies. When we look at different observer frequencies, we see different distances, because a photon, for example, emitted at a redshift 17 when the universe was roughly 1/18 its current size, will appear not at 21 centimeters, but at a wavelength of 21 centimeters times 18, or a frequency of 1.4 gigahertz divided by 18, or 78.9 megahertz. So it turns out that this is the predicted, this is the prediction for the angular power spectrum for the circular polarization at different frequencies. And if you look at these amplitudes and compare with what might realistically be done in the next few decades, it's not completely beyond the pale. So this is actually a prediction that experimentalists might actually be able to go for. So I think I will stop here. So what I hoped to tell you here is about a number of different things that I and my collaborators have been thinking about that are centered somewhat around the idea of looking for chirality in the universe. You know, signatures of parity breaking that are from new dark matter physics, new dark energy physics, new baryogenesis physics, new physics responsible for inflation in cosmological observables. And in the process, we've developed a number of mathematical tools, including something that we call total angular momentum formalism, that turns out to allow dramatic simplifications for the calculations of observables, because in cosmology and in astrophysics, we observe a spherical sky. You know, we look out into the universe and we see a spherical sky, and it turns out that although the universe, you know, we're not at the center of the universe, it does turn out that we are at the center of the observable universe. And so spherical coordinates are a natural coordinate system to use to describe the observable universe. And this total angular momentum formalism turns out to be a great substitute for the standard Fourier analysis that people usually use when they discuss normal modes of various types of systems. It's especially useful when we have vector or tensor modes, higher spin fields, or observables that are a second order or higher in perturbation theory. And so one of the things I told you about was the circular polarization of the cosmic microwave background. This turned out to be interesting, I think, as a proof of principle or for academic purposes. We showed that a chiral gravitational wave background can imprint its chirality onto the chirality of the cosmic microwave background if there is cosmic parity breaking. Again, that is probably of academic interest. We found that there's an elegant and compact formal, that this elegant and compact, this formalism, total angular momentum formalism, the killer app for that actually turned out to be these calculations of observables for pulsar timing arrays and astrometry. And we've also started to think about the circular polarization of the 21 centimeter radiation from the cosmic dark ages. And this is not completely academic. The predicted amplitudes are very small, but conceivably detectable. So I am happy to take questions.
Okay, thank you very much for a nice presentation. We have at least one question right now. So Farid Dinawaz.
Okay, do you hear me?
Yes.
Yep.
Thanks for your good presentation. I was thinking about the relation between these chirality breaking events in the universe and what we saw in the standard model. Could you please explain more about the relation between these two topics? Are there any relation between them or any separated objects such stuff?
Can you say the question again? I think your sound went out.
I asked about the relation between the chirality breaking events in the standard model, which we saw, such as you told in your introduction about the asymmetry between right-handed and left-handed particles, and what you saw in the universe by this stuff.
Oh, okay.
Are there any relation between these two topics or not?
I wish. I wish there were, but I haven't been able to think of any, and I don't think that anybody else has thought of any direct relation. However, some people have constructed models that tie, attempt to tie the baryon asymmetry to the chirality of the gravitational wave background. So there are models that discuss baryogenesis in terms of, say, the evolution of some scalar field that then has a, say, Chern-Simons coupling to the gravitational field. So in those models, the baryon asymmetry is related to the chirality of the gravitational wave background. And in principle, given that we see protons as opposed to antiprotons, that would tell you that the gravitational wave background should be right-handed as opposed to left-handed. Those are papers by Stefan Alexander and Michael Peskin and their collaborators. I think Jim Gates might have been on some of those papers as well. Yeah, so people thought about that, but that's the only thing I can think about that I've seen.
Okay.
Can I ask a question on that?
Do you have something to this question or?
This question.
Okay.
That why is it that you consider a chirality of gravitational background, but not, for example, electromagnetic? So there are magnetic fields, there are probably helical, if the whole universe is helical.
That's a very good question. We just haven't gotten around to it.
Yeah, your first part for scattering cosmic microwave on cosmic microwave, yes? That is a field which definitely exists, of course, but it's very small. So what about scattering on cosmological magnetic field, or maybe even galactical magnetic field, which is just background to you?
Yeah. So the paper I wrote with the first of two papers that I wrote with Keizuke Inomata on the circular polarization of the cosmic microwave background, we wrote down formulas for vector perturbations, which are what magnetic fields are, but we didn't follow through. We just haven't gotten to it yet. But it's a very good question.
There must be something in galaxy, at least, because we know it's magnetic.
Yeah.
So if
it does seem much bigger.
Yeah, it's much bigger field, so you will have some initial measurement before, so to say.
Yeah. Well, the other good thing about that is we do have some ideas about how the magnetic field in the galaxy looks, and so we should be able to cross-correlate the known features of the magnetic field with the observations. Yeah, that's a great idea. Just haven't gotten around to it.
Okay, let's move to the next question by Zhou. Zhou. I don't know how to pronounce correctly. Go ahead.
Oh, can you hear me?
Yes.
Yeah, I have a probably simple question. So you said the pulsar timing arrays is very close to observing the stochastic gravitational waves. But I think it is determined by the sensitivity of the pulsar timing arrays and the rate of the supermassive black holes in the universe. But how well do we know the rate of the supermassive black hole merged in the universe?
I would say that if you look at the theoretical predictions, there's roughly an order of magnitude uncertainty in them. And the current upper limits are actually ruling out some of that parameter space. There's some people who are surprised that they haven't seen anything yet. And then I think it depends, that lower limit, I think depends on who you ask. Basically, the idea is that we know that some fraction of ordered unity of the mass in supermassive black holes arose from accretion, because when gas accretes onto supermassive black holes, it emits radiation at all frequencies, and we know what the the energy density in the universe is due to emission onto supermassive black holes, and it's comparable to the mass density of supermassive black holes. But we also know that every galaxy, almost every galaxy, it seems, has a supermassive black hole. We know the galaxy is formed by merging of two smaller galaxies, and so it's almost, it stands to reason that the amount of mass that comes from supermassive black hole mergers, the fraction of the mass in supermassive black holes that comes from supermassive black hole mergers should also be of order unity. So whether it's 10% or 90%, no one really knows, but if it was much less than 10%, I think would be very surprising.
I see. Yeah, a follow-up question is, I think we don't quite know how do the supermassive black holes merge yet. There is something called the last parsec problem, and could the observation by pulsar timing arrays give some hints of the problem?
That's a very good question. It turns out that Last parsec problem is not a problem for supermassive, for the gravitational wave background. And the reason is that the gravitational wave background is dominated by the mergers of the most massive supermassive black holes, like 10 to the 8, 10 to the 9 solar masses. The signal is very, very heavily weighted to the most massive supermassive black holes. And those massive objects do not have a last parsec problem.
Okay, I mean that is for the smaller mass.
Yeah, it's a bigger for the smaller mass black holes.
I see. Thanks.
Okay, next question, Tanmay Vachaspati.
Hi, Mark. Good to see you.
Hi.
So I was a little confused by your earlier slides where you had PAB and phi AB. That formalism seems just like you'd use for Faraday rotation.
Yeah.
But Faraday rotation gives you linear polarization, which is just rotated.
Oh, not Faraday rotation. What's it called? Is it Faraday generation? I forget what the term is.
So how is that different from Faraday rotation?
Faraday rotation, in Faraday rotation, I have a linearly polarized photon. And then it propagates through a medium in which the velocity, so if I have a linearly polarized photon in this direction, I can decompose it into something in this direction and something in this direction. Okay, let's do it this way. There's polarized here, 45 degrees with respect to X and Y axes. Now, if the index of refraction for the Y component is different than the index of refraction for the X component, then it gets circular. It gets the linear polarization gets rotated. Okay, so that's Faraday rotation. Now this is a little different because I have a circularly polarized photon, and what happens is that the index of refraction is different for modes that are Q, which linearly polarized in this direction versus this direction, versus those that are polarized in this direction versus this direction. So in some sense, Faraday rotation is what happens when you have a linearly polarized photon that propagates through an index of refraction that has a spin 1 component, and I forget what the term is. Is Faraday generation? I should know this.
Yeah, okay. Anyway.
But if I have linearly polarized light that propagates through a material that has a spin 2 anisotropy, then it generates
circular polarization. I see. Okay, thanks.
Okay, next question, Masood Chokri.
Hi. I want to get back to the question about the magnetic field background. Probably my question is because I'm ignorant of many things in cosmology. But as far as I understand, the universe as in general, in larger scales, should be rotationally invariant, yeah?
Yep.
So if there is a magnetic field background, doesn't it break this?
Yes, that's a very good question. So to a first approximation, the universe is homogeneous and isotropic, but that is an approximation. It's not an exact homogeneity and isotropy. You know, there are some places where there are lots of galaxies and other places where the galaxy density is smaller. So there are density fluctuations in the universe, and those break what would otherwise be an isotropic and homogeneous universe. So what we say is that the universe is, what we now hypothesize is not that the universe is perfectly homogeneous and isotropic. We know that it's not perfectly homogeneous and isotropic, but we hypothesize now that it is statistically isotropic and homogeneous. So that although there are fluctuations here and there, on average, there's no preferred direction. So it's conceivable there could be a magnetic field that points in this direction over here, but then points in some other direction over here, some other direction somewhere else, and some other direction somewhere else. So that averaged over large enough volumes of the universe, there is no preferred direction of that magnetic field.
Thanks.
Okay, I don't see any questions from the audience, but I sort of had something that was suggested by Tanmei's question. I'm kind of also confused about the circular polarization. One way of looking at the linear polarization, in fact, is just taking two circularly polarized waves with a fixed phase difference between them. And that's basically, but the same constant velocity. Now, if you suppress one of the polarizations, for example, you produce only one polarization, then it becomes circularly polarized. And that happens, for example, in a magnetic field. So that is Faraday rotation. So whenever the light is propagating through a magnetic field, it becomes circularly polarized. So I'm not sure your explanation was sort of clear, the difference between your circularly polarized and Faraday rotation.
Wait. Whenever light is propagating through a
magnetic field or any other active media, it becomes circularly polarized in that medium. Of course, you might say that if it comes from the outside, one linear polarization, at the end, it comes with a different angle polarization, so it's still linear polarization. But in the medium, it's actually circularly polarized. So, and it depends sort of also on where we live in the medium or outside of it.
Wait, I don't think that's right. So suppose I have a medium that has a plasma with a homogeneous magnetic field that is along the line of sight.
Yeah, and the plane polarization will be constantly rotating as it moves through.
That's right, the plane of linear polarization, but after it gets out, it'll still be linearly polarized.
Yes, that's true.
Yeah.
But this active media has circular polarization in the medium. So
that's right, but it does not necessarily induce a circular polarization in the. It does not necessarily induce a circular polarization.
Right, unless it absorbs one of those circular polarizations and the other one is unabsorbed. So essentially the difference is the sort of the coefficient of, well, refraction really. That's all it is. But there's a huge difference between the two. That's what I'm trying to say.
I think that'll be the complex. I think what you're talking about is the complex component of the index of refraction.
It is, if this is propagating in the z direction, it will be imaginary part of 1,2 component of the electric constant or the polarization tensor.
Yeah.
I have a question too. I don't know, can you hear me? I sent you a note, Igor, but you didn't seem to notice it.
I was probably asking and didn't notice, sorry. Go ahead.
Hi, Marc, it's Lawrence.
Hey, how's it going?
Pretty good, how are you doing?
Pretty good.
Good. Okay. I was actually had a comment on that, on what Igor just said, but I think you guys resolved it. I think at any one point you always measure linear polarization. But anyway, that's a different issue. I was also thinking about axions, which I think about a lot. Now they induce a Faraday rotation, but they could have a quadrupole moment in their distribution. But I'm assuming that they because the coupling is smaller than alpha squared, that it's even smaller than the unobservably small effect you would look at. But have you thought about it at all? I was gonna email you and ask you that, but I figured I'd ask you now.
So that's actually, so suppose that scalar field, that axion field, is the quintessence field. And suppose that the quintessence field is slowly rolling down potential. I mean, this is the canonical example that we use, actually. You know that. So, so there's a phi FF dual coupling. So if that scalar field couples to FF dual of electromagnetism, then that gives you a Faraday-like rotation. Polarization.
But I'm not thinking about that so much. I'm just thinking, look, there's an axion dark. If axions are dark matter and there's a distribution and they have a quadrupole moment of the galaxy.
Oh, so if they are the dark matter. Yeah, people have been thinking about that. I haven't followed.
Okay, well, I'll follow up with you. But
people have been thinking about that. Look for, I don't know if it's in there, but the first place I would look is recent papers by Anson Hook.
By who?
Anson Hook.
Okay. My assumption is based on your formalism. If I look at it at the relevant E.B terms, it's probably unobservably small just because the axion couplings are so small. But it is amplified by the density in the galaxy.
I think if you're talking about a QCD axion, it's going to happen. But if it's an ultralight axion, if it's an ALP, an axion-like particle, axion-like particle, or an ultralight axion field. So if it's a dark matter that has scale that has a de Broglie wavelength comparable to the size of the galaxy.
Yeah.
It's a coherent field, then there might be something there.
Yeah, I was wondering. I've been thinking about that lately. Okay, and I still suspect it's small, but I didn't know if you'd looked at it. Okay, it's nice to see you anyway.
Good to see you.
Okay, we have another question from Henry De Jong. Hope I pronounced it correctly. Go ahead.
I just wanted to ask, besides the pulsar timing array, could you use the positions of the pulsars to also detect the gravitational wave?
Hold on, can I ask you a question? Are you in the Netherlands?
No, I'm here in Arizona.
Do you write papers on, do you work on, tell me what you work on. I think I've seen your name in connection with something I thought about once.
Well, I write papers, but it's just for a local organization. I teach astronomy at a local community college.
Okay, there's a Dutch physicist with the name De Jong who writes papers on, what's it called? Kinetic theory, the Smoluchowski coagulation equation, things like that.
No,
Okay.
that's not me. If he has an E on the end of the name, though, like mine, he's probably a relative.
Oh, yeah, I think he does. Okay, so what's the question?
Can we also use, besides the timing array, can we use the positions of the pulsars, even though it's a smaller sample size, to detect the gravitational waves?
That's a great question. My understanding is that we don't localize the pulsars that well. So the amplitude of the scattering of the displacement is a micro arc second at best, which is very, very small. Cannot be detected from the ground, might be detectable from space. And it's the kind of thing that the Gaia satellite has been looking for, and actually not too far below the Gaia satellite sensitivity. The problem is that the Gaia satellite was not designed to do this, and so there's systematic effects. They measure the position of stars in that patch of sky very well, and then that patch of sky very well, but it's hard to compare the measurements there with over here, which is what you need for this particular thing. So the pulsars, you just don't measure the locations well enough. I mean, another possibility is, I think, you could get the angular sensitivity with VLBI measurements of quasars, but I don't think but pulsars are observed because they pulse. And we know they're coming from over there, but I don't think we can localize them that well.
Okay.
They're observed at radio frequencies, and the telescopes are Arecibo. That thing looks like a football field. So I think the angular resolution just isn't good enough.
Okay, thank you.
I don't think we have other questions. If I missed anybody in the chat session, let me know, because I don't think I see anybody else wanting to ask a question. So using this opportunity, I would like to thank Marc again for a nice presentation, for creating a lot of discussions. And we will be finishing unless there is anybody else.